For this example, we want to find the domain of this function, g of f of x, when we're given that f of x is 1 over x, and g of x is x squared plus 4. So we're finding the domain of g of f of x. So again, when we are finding the domain of a composition function, we need to figure out what, if anything, makes the inside function undefined. Because if the inside function is undefined, then we have no output to plug back into g. So that's going to be a value that is restricted. And then also we have to figure out what restrictions there are on the outside function so that we can't make the inside function equal that, so that there's no problems with the outside function g. So in our function f of x, we have 1 over x. We know that the denominator cannot be 0, so x is not allowed to equal 0. For g of x, however, this is a polynomial function, and polynomial functions have no domain restrictions. So in this case, the domain is all real numbers. So we don't really have anything that we need to worry about here. So if we're trying to find the domain of this, g of f of x, we know that there are potentially domain restrictions on f of x, and that's x equals 0. So that's going to be one restriction on our domain. So it's the set of all x such that x cannot equal 0. And so if x was 0, right, we get an undefined value, so then we would not be able to evaluate g at whatever the output is, because the output's undefined. But then we also have to consider what makes this function 0, right? If there's some input of f that output for f that makes this undefined, that also can't be included. But luckily, this whole thing has no domain restrictions, so whatever my output is, no matter what, whether it's a fraction or a decimal or an irrational number or a whole number, whatever it is, I can plug it into this function. So whatever my output is not going to be a problem in this, which means x cannot equal 0 is the only domain restriction on this entire function. So that is our domain.